In this short video, I will talk about periods of complete intersection cycles. Okay, so let's start with the definition of what is a period of algebraic cycle. Consider X be a smooth projective variety of dimension n, and Y be any algebraic subvariety of dimension k. So for us, a period of Y will be an integral of the following form. It will be the integral of a differential form omega over y. This differential form has to be of degree 2k, and it will be regarded as an element of the 2k's de Rham cohomology group of X. So it will be a closed form. An example of a period of an algebraic cycle is the period of top forms over the projective space. So let us start considering a generator of this space of top forms. So we know that this space of top forms is in fact a one-dimensional space, which it is concentrated in the middle part of the Hodge decomposition of this cohomology group. And moreover, this middle part can be regarded as a chief cohomology group, which can also be regarded as a check cohomology group. So we will describe a generator of this space in the following way. Take this metamorphic form omega over the product of all variables of the projective space, where omega is just this alternating n form, which can also be written in this format. Once we write this form, this differential form in this format, we see that if we restrict ourselves to any chart, for instance, the chart x0 equal to 1, we will obtain the usual top form of the affine space. And moreover, this description is an element of the nth check cohomology group with respect to the usual open covering U of Pn, right? Where U is the standard open covering, which is just given by these open sets Ui, where the coordinate xi is different from 0. So this is an example of a generator of a top form. So it will be a form omega living in the 2nth group of Pn, and we can compute its period. So its period is just given by this formula. Is essentially a sine times 2 pi I power 2n. In order to compute periods of complete intersection cycles, we will need first to describe a special map, which we call the coboundary map. So let us introduce it as follows. So consider now X to be any projective variety smooth of dimension n plus 1. And take Y to be the intersection of X with a hypersurface given by homogeneous equation f equal to 0 inside some embedding of X in a projective space, in such a way that this hypersurface Y is smooth. Consider now the following long exact sequence, which is usually called Geisen exact sequence or Lera exact sequence. This exact sequence is in fact a sequence of morphisms of Hodge structures. And so each of these maps is compatible with the Hodge decomposition of each of these cohomology groups. This sequence can be induced as a long sequence in cohomology or hypercohomology induced by the following short exact sequence of complexes, which is usually called the Poincaré residue sequence. Since the map tau, which we want to describe, is the coboundary map induced by this short exact sequence of complexes, we can give a nice description of this map in terms of hypercohomology. And moreover, since we have a nice description of the Hodge decomposition of each of these, or of the Hodge structures of each of these derived cohomology groups, in terms of check homology, we can in fact compute this map tau in terms of the check homology description of each pieces of the Hodge decomposition of these groups. So how do we compute the description of tau in terms of the check homology groups is as follows. So consider omega to be a check code chain inside X of n forms, such that when we restrict omega to Y, we obtain a check cocycle, right? And so it will represent an element in the check homology group. Consider now omega bar to be a check code chain over X of the chief of n forms with logarithmic poles along Y, and be such that this omega bar is equivalent or congruent to omega wedge df over f module the spaces of check code chains of n+1 forms over X. So if we look at the construction of tau as a coboundary map, this is exactly what we are describing here. So we're starting from some covering of X, which restricts to a covering of Y, right? In each of these open covering, of these open sets in this covering, we are taking a differential form omega, right, an n form, and we're assuming that this covering is given in such a way that we can lift each of these forms to X, right? Then we're trying to find an element omega bar such that the residue of omega bar is our omega restricted to Y. This is how we construct omega bar. And then in order to obtain tau as the coboundary map, we just need to take it as the check differential of omega bar. This is the usual construction of a coboundary map in check homology, right? So we have this nice description of the coboundary map tau, but on the other hand, we know what is the topological description of this map tau. It is just a cup product with the usual polarization of X, given by, for instance, this embedding inside this projective space. And so, using this other description of the map tau, we can understand how is the relation between the period of form omega inside this 2n random cohomology group of Y, and the period of tau omega inside this cohomology group of X. And this relation is given as follows. The period of tau omega is minus 2 pi I, the period of omega. So now we're in position to state our main theorem, which is about how to compute the periods of complete intersection cycles inside a smooth hypersurface of the projective space. So the theorem is as follows. Consider X be any smooth hypersurface inside a projective space. We assume further that the dimension of this hypersurface is even. and that is has degree d and is given by a homogeneous polynomial f equal to 0, where f has degree d. Moreover, assume that the equation of x can be written in this special format. It can be written as a sum of products fi times gi, where each of these polynomials are homogeneous, and so we can define z to be the zero locus of all the fi's equations appearing in this above factorization. So certainly this variety will be a subvariety of x, but what is non-trivial and we are assuming is that the subvariety is in fact a complete intersection subvariety of the ambient projective space. And so, since it is defined by n over 2 plus 1 equations, it has to be of dimension n over 2. Consider now h to be the vector of polynomials h0 up to hn plus 1, which is given by ordering these factors appearing in this equation here. f1, g1, f2, g2, up to fn over 2 plus 1, gn over 2 plus 1. Then, for each homogeneous polynomial p of degree d minus 2 times n over 2 plus 1, we will have a formula for computing the period of omega p over z, where this omega p is any element of the nth, the RAM cohomology group of x, and more precisely, it will be an element of the n over 2 piece of the Hodge filtration of the nth, the RAM cohomology group of x, and the formula is given as follows. So we have this first factor, which it's just depending on the dimension of our hypersurface, and the second factor, which is also depending on the degree of x. But the non-trivial information of this period is contained in this middle part, this number c, right? Note that these other two factors are independent of our choice of the polynomial p and our choice of the complete intersection cycle z. These are just depending on x, right? So the non-trivial information is this number c. And how do we compute this number c? Is as follows. So as I said before, this omega p is just an element of Griffith's basis, is the residue of this meromorphic form. It will land in the middle part of the Hodge decomposition, of the Hodge filtration. And C is characterized by the following property. This is the unique number, the unique complex number, which satisfies the following equation. This equation is the following. It will satisfy that the product of the polynomial p times the determinant of the Jacobian matrix of the vector h, which is also a polynomial of degree d minus 2 times n over 2 plus 1. So this product is an homogeneous polynomial of degree d minus 2 times n plus 2. And it will be congruent to some number, a unique number, times the determinant of the Hessian matrix of f, which will also be an homogeneous polynomials of degree d minus 2 times n plus 2. And this congruence has to be taken modulo the Jacobian ideal of f, which is the ideal generated by the partial derivatives of f. In other words, the non-trivial information of the period of the form omega p over c is contained in this factor, which is relating the coefficients of these three polynomials. One of these polynomials is containing the information of the differential form. This other polynomial is containing the information of the algebraic cycle, and this other polynomial is containing the information of the ambient hypersurface X. Okay, so let's give an idea of how is the structure of the proof. I won't give all the details, so you can read the textbook. So the idea is as follows. We start considering a chain of subvarieties, C0 contained in C1, C2, and so on, until Cn over 2 plus 1, which will be equal to the ambient projective space Pn plus 1. In such a way that each Ci is a smooth hypersurface of Ci plus 1. So using a trick, we can argue that we can always assume that Ci is in fact given by the following equation. It's just taking the zero locus of the last equations defining Z. Then we are in position of applying successively the co-boundary map, which is just a map relating these two check homology groups, right? So using this map, we will construct inductively the forms omega p tilde power to I plus 1, which is just applying tau to the omega p tilde power to I, and where we start from our omega p, right, which was the form that we took above C. So after applying this co-boundary map n over 2 plus 1 times, the result is this omega tilde n over 2 plus 1, which can be computed explicitly in check homology as this meromorphic form here. The difference is that this top form, which is a top form of the projective space Pn plus 1, is not given anymore in the usual or the standard open covering of the projective space, but in this other open covering UF, which is just is known as the Jacobian covering of Pn plus 1. And it is given by these open sets Bi, which are defined as the set of points where the partial derivatives of f are non-zero, right? So this is a covering of the projective space because X is a smooth hypersurface. And so since we have this top form here, we want to compute its period, right? Because the co-boundary map already tells us how to relate the period of our original form omega p over C with the period of the resulting form omega tilde n over 2 plus 1 over Pn plus 1. But in order to compute that period, we need to relate it to the usual volume top form in Pn plus 1. So how do we do that? We need to change our standard covering to this Jacobian covering. And this can be done easily by applying the following map. So consider phi to be the map given by the partial derivatives of f. This is a finite morphism of Pn plus 1 to itself. And the pullback of the usual volume top form of Pn plus 1 can be computed, and it's just given by this formula. And so using this pullback description, we can compute the period of this top form given in terms of the Jacobian covering. And now the number C appearing in our period formula is just the number relating these two polynomials, right? And we have to know in order to relate the period of omega tilde n over 2 plus 1 with the period of the pullback of the volume top form of Pn plus 1. And this completes the sketch of the proof. Finally, I want to introduce some consequences of this period formula. So the first consequence is that we can, in fact, compute the cohomology class of any complete intersection algebraic cycle C in the following way. So the cohomology class of C will be given by this formula. So when we look at this formula, we see that this right-hand side corresponds exactly to the primitive part of the cohomology class of C. And this is given by our period formula, right? Our period formula is telling us, in other words, that the primitive part in terms of Griffith's basis is given by the determinant of the Jacobian matrix of this vector H, which whose coordinates are just the entries of this factorization of our polynomial f. And well, this extra factor comes from the period formula, and on the other side, the only missing part in the whole de Rham cohomology group is the orthogonal part to the primitive de Rham cohomology group. And this orthogonal part is one-dimensional. It is known that it's generated by the polarization, and it's not difficult to compute the multiple, which is just this quotient of degrees. Okay, so a consequence of this theorem is that we can use this description of the cohomological class, for instance, to compute intersection numbers of algebraic cycles, and also we can determine whether a given combination of algebraic cycles is trivial in primitive cohomology or not. So consider two algebraic cycles, delta and mu, which are just a combination of cycles Ci, Yj with integer coefficients, and we will assume that these algebraic cycles, these prime algebraic cycles that we're considering here, they are of dimension n/2, and moreover that they are complete intersection cycles. Then we have a criterion to know when the cohomological class of this algebraic cycle is trivial in primitive cohomology, or in other words, it is a multiple of the polarization, right? Which is the cohomological class of the intersection of X with a generic Pn/2 plus 1. This happens if and only if the following polynomial, which can be computed explicitly in terms of the equations H of each of these complete intersection cycles Zi, right, where this Hi is our vector H associated to the complete intersection Ci. And so the criterion is the following, right? This class is trivial in primitive cohomology if and only if this polynomial, which can be computed explicitly, is an element of the Jacobian ideal of f. Moreover, another computational consequence is the following. So consider C be the unique number such that it satisfies the following algebraic equation: the product of these two polynomials p delta times p mu, which were defined before, is congruent to C times the determinant of the Hessian matrix of F modulo the Jacobian ideal of F. So this unique number that satisfies this equation is the only information that we need in order to get a formula for computing the intersection number of these two algebraic cycles. And the formula is the following. So we obtain a nice formula which can compute the intersection number of two algebraic cycles in terms of the explicit defining equations supporting each cycle, right? So this number C is depending on the equations of each Ci, each Yj, and the equation of F. So for instance, we know that this number, which a priori is just a complex number, is in fact a rational number. It always has to be a rational number. And so these are two consequences of this theorem, and there are more consequences that you can see in the textbook.
In this video, I'm going to talk about chapter 9 of my book with Roberto. It is about Gauss-Manning connection from topological and algebraic point of view. So first, what is Gauss-Manning connection from a topological point of view? Let's assume that we have a family of smooth projective varieties. So its fibers will be denoted by xt. So here is the parameter space capital T, and our point, let's say here T, then we will have the M cohomology of xt. And the rank cohomology with complex coefficients. If we ignore torsions of singular cohomology, inside this cohomology, we have also singular homology. So we have this cohomology bundle, and this cohomology bundle have this very special flats whose images will be here. This gives us, these are going to be actually the flat section of Gauss-Manning connection. So in a small neighborhood U of T, we can find the sections S1, SB such that any order holomorphic section U can be written as a combination of SI with FI being holomorphic functions in U. And then we define this connection on the cohomology bundle, which send this sum of Fi Si to the Fi tensor Si. So by definition, Si nabla Si is 0, and so this means that Si is a flat section. Before defining the algebraic Gauss-Manning connection, we have to define what is cohomology bundle in the algebraic geometric framework. For this, we need to define the sheaf of relative differential forms. So these guys for us will be 0. And it turns out that we have a complex of the relative differential forms. And so when we have the complex, then we can define the relative algebraic rank homology in a similar way as the non-relative case. Remember that for our computational purpose, we take a covering with affine open sets. This will be a good covering for us because we are using differential forms. And then we form this double complex. And then going up is delta, going to the left is t, and then we define this capital T operator from Lk to Lk plus 1. Remember that this was L0, this was Ly, this was L3, and so on. And the algebraic rank homologies is just the the total, the cohomology of this usual complex L dot D. Now, one very important fact that everything is done over an arbitrary field k of character 0. And when we have started from a smooth projective variety over k, then the relative theorem cohomology is a free shift of finite rank of OT modules. And in a more geometric language, they are sections of a vector bundle, which we call it a cohomology bundle. In the book, we have presented two proofs for this fact, the topological and algebraic proof, and I will skip the proofs here. Let us now try to define the algebraic Gauss-Manning connection. So we have defined the cohomology bundle as a relative theorem cohomology. The sheaf of differential one formed in T is algebraic because T itself is algebraic. So what is this knot that we already saw in the topological context? For this one, we have, for simplicity, we will take T aspect of some ring, and we will distinguish these two differential. So dr will be the differential of the relative theorem cohomology, and why we put r? Because for this dr, the elements of r are constant. Whereas when we take differential forms on x itself, the constant of the differential form will be elements of the field. So these elements will be no more constant. Remember that we defined our relative theorem cohomology using this double complex. From another side, we have this double complex of differential forms on x, and we have a canonical projection from this one to this one here. So we take element omega 0 plus omega 1 in H M theorem x over t, and we take a representative of this one in this double complex, and we denote it by omega 0 check plus blah 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 omega n check. So we have a differential of the relative case of omega equal to 0. When we apply the now differential non-relative one, dx of omega hat will be an element like this, and this must be 0 in the relative version of differential form. So this means that omega hat I will have this beta I alpha I part, and then here we'll have alpha I in omega 1. And we simply map this element to element here, replacing the wedge with the tensor sign. And now we are claiming that this is almost the image of the Gauss-Manning connection of omega. For this, we have to check that the image of the we have to check that this happens, and remember that these new differential forms, they have coefficients in omega 1t, and in this way we can transport this guy into an element in omega 1t tensor with h m theorem x over T. In order to prove this identity, we use the fact that omega t or omega 1 t, which are differentials of the ring R, are generated by exact form. And from this exactness, we will just use the closedness. And then we start from this identity, and then the first dx, we just substitute the definition that we had here. And assuming that alpha us are closed, then we will have this this identity, and this will imply that identity in the omega 1 t part tensored with d, the relative differential operator of the element that we have get, is 0. And finally, we define the algebraic Gauss-Manning connection with this as this one, appearing this minus 1m there. The fundamental property of the Gauss-Manning connection is this theorem, which relates it to integrals, and that is why the name of Gauss appears. So these integrals will be holomorphic functions in T, so we can take its differential, and its differential will be the integral of delta T of the value of naught over omega, remembering that the integration is not taken in the omega 1 t part. These are just constant, and it is taken in the cohomology bundle part of the element. So the same theorem with different language used is say that the Gauss-Manning connection that we introduced in the beginning of our video is the same as the algebraic Gauss-Manning connection that we discussed. And one important part of the proof is this proposition 31 in my book, which is basically the same equality that we wrote in the framework of affine varieties. So in affine variety, we don't need really to use hypercohomology, because variety Hodge theorem elements of the rank homology are already represented by algebraic differential form. So let's close this video with some fundamental properties of the Gauss-Manning connection. One of them is the integrability. So actually any connection will induce this kind of maps, which are defined by this, and the composition of two consecutive such maps is 0. This is called the integrability condition. The next important property is the relation of Gauss-Manning connection with Hodge filtration. So in a similar way, we'll have Hodge filtration of the cohomology bundle, and it turns out that the Gauss-Manning connection of Fk goes to Fk minus 1. So it's a kind of pushing forward. Remember that Fk was inside Fk minus 1, and blah blah blah, and then there is everything is inside F0. The proof of this fact is just the definition of the Gauss-Manning connection. Remember that we take the representative, we make its dx, we go forward, and when you look at this element, we will already realize that that if we were in omega k, then the image here, if you have eta k check, and above it everything is 0, is here above this one everything is 0, and so from fk we have jumped to fk minus 1. Few other properties of the Gauss-Mann is gathered in this proposition. So the polarization that we called it theta is a flat section. So this is a kind of natural. It's compatible with all our knowledge of topological Gauss-Mann connection, because remember that polarization was the cohomology class of the hyperplane section, and this is in singular cohomology with integer coefficient. And since we have defined the Gauss-Mann connection using the usual differential, it is natural to expect also this second property, which is derived from the similar property for the differential d, and also the fact that an Aula sends the primitive cohomology to itself, and so it will respect the Lefschetz decomposition. A more elementary version of Gauss-Mann connection is presented in chapter 12 of my book. It contains a historical account of the Gauss-Mann connection, which is basically quite like this derivation of some integral, which depends on some parameters. It goes inside. And this remember that this was written in 10 minutes ago as something like this. Nabla omega delta. For example, in this exercise, we consider just a family of elliptic curve y px, and you see that px depends on 3 parameters. So we take the differential of the integrals over some cycle with respect to these 3 parameters, and it turns out that this dx over y, x dx over y are bases, are 2 sections of the cohomology bundle here, such that at each point they form a basis. So we can write this differential here. I have what this, let's say in the usual language that I explained it. There's a tensor here, and so here we have differential 1 form in omega 1t, and then the integrals here. And if I want to write down this without the integral range, so without this integral range, we could just remove the integral sign. Here put px just y, and here put tensor sign, remove integral, and that is the Gauss-Mann connection in the sense of Gauss. I hope you enjoyed this video.